so finishing up chapter 3 here, we're going to start introducing some other functional groups and how they're going to adjust the names, or just how we go about naming them, that is. So I just have a few up here. So and below are what we would consider our common names. They're not necessarily IUPAC, and we will make sure we cover how to do that. Now, it turns out the bromine one, to add the rules, is actually kind of simple by comparison to most of these, and that really is simply because bromine and chlorine and our halogens are just considered substituents. They don't change the backbone. Thus, since it doesn't really change how it works, we're just going to treat that as a substituent. So naming this follows the same rule. So I have my backbone going right along here. And I would actually number from down here because I got a substituent on the first carbon. So 1, 2, 3. So 3. So our IUPAC name, we have a methyl group, we have a bromo group. Bromo would come first. So this one is also called, I'll put it down here, 1 bromo, 3 methyl, and it is 1, 2, 3, 4 carbons, so butane. And just follow the rules. The halogen does not necessarily change any of the rules that we've introduced, so just treat it like a substituent. Now the alcohol and amine will, so we're going to add to our rules some next. Alright, but first thing we're due, since we just introduced those halogens, is talk about how we classify them. Now this doesn't affect the nomenclature, it just is actually a classification. And to a degree, the type or the classification does affect chemical properties. Now, not a huge amount on our halogens, but they will chemically behave slightly different. We will find that certain reactions are just not allowed with tertiaries, where they are allowed with alkyl halides. All right, now, what do we mean by the primary, secondary, tertiary? When you see those names, they refer to the carbons that are attached to the carbon the halogen's connected to. So you'd find your halogen, and then you'd look at the very next carbon, and you'd want to know how many carbons it's attached to. If it's attached to 1, it's a primary carbon. If it's attached to 2, it's a secondary. And 3 is a tertiary. And of course there won't be anything more than that because there's only 4 things able to connect to a carbon. Alright, now common names get used a lot on our smaller and simpler alkyl halides because basically what we end up doing is, you can think of any alkyl halide as having a organic compound attached to a halogen. Well, if I can name this as if it's a substituent and then just name the halogen, I've generated a common name. So methyl chloride really is just saying there's a methyl attached to a chlorine, ethyl fluoride, ethyl group to a fluorine, isopropyl iodide, isopropyl, and then the iodide, and then sec-butyl bromide. But those are common names. Now, we're going to see them a lot, and we do want to get comfortable figuring out what those names are, but if you're asked to provide a name, it's typically we're going to want the systematic name or the IUPAC name. And there we're just naming these as if they're substituents. And chloro and fluoro, we didn't bother to number the backbone because the halogen must be on the first carbon. The isopropyl, once we've got the 3 carbons, we're pretty much going to have to number it, so that's why it's 2-iodopropane, and that's also why we have 2-bromo on the last one. So the numbers are necessary when there's more than one place to put it, and you'll find that common names generally don't have numbers at all. Okay, so our rules, we're going to follow them exactly as we did before. So what that means is we will find our longest continuous chain of carbons, and we will number our backbone to get the lowest possible number for any substituent, regardless what that substituent is. So since we have the bromines at this end, we have 1, 2, 3, 4, 5, 6, 7. And on this one, I could have my backbone zigzag. And while, yeah, there are 2 methyls down here at this end, those would be on the second position if we started from the left, yet the chlorine is on the first carbon. So that's why that gets the number 1. 5, 6. So 1-chloro-6,6-dimethyl. On our rings, if there was just one, and I don't have an example of that, but if I just had a 5-member ring with a chlorine, we would just call that chlorocyclopentane, no number, because it's one substituent. If there's 2, we're going to number it based on alphabetical order. So ethyl is alphabetically before iodo, so that's the 1 position, that's the 2 position. And on this one we have 3, so we're going to number it the shortest possible path to get the lowest possible number, so 1, 2, and 4, and then we're going to name it based alphabetically. So bromo comes first, chlorine, and then the methyl group. So no changes of the rules. We've just added chlorine, bromine, fluorine, and iodine to our nomenclature. All right, next functional group we're looking at is ethers. Now we will find common names are incredibly common, or very, very used. Matter of fact, diethyl ether here is so common, if you ever see something referred to as just ether, that's the one they're talking about. That is really because that particular compound was used in medical field for a long time as an anesthesia. And we use it as a solvent, or a very common go-to solvent, in some of our later reactions. So you will see the phrase ether, and they are talking about specifically about this one. But technically both these names, the dimethyl ether and diethyl ether, are common names. If you see a substituent name and then a space and then just ether, that is a common name. And they actually, we do see stuff like this. So I'd have a CH3 to the O, CH2, CH3, which is kind of like a mixture between these two. And that happens, and a common name would be ethyl, methyl, ether. Name each substituent separately. And typically on those common names, when we have those 2 different ones, we do actually list those 2 substituents alphabetically. But you will find on common names, that's not a hard rule. It's perfectly likely to find this listed as methyl ethyl ether. All right, but those are common names. And this is just some other examples of it, but it is all common names as if we're naming these guys as substituents off of an oxygen. Methyl ethyl, ethyl and ethyl. This guy would be no, that's not tert-butyl. That's isobutyl. That's tert-butyl. And we have isopropyl and sec-butyl. And that weird one is actually isopentyl, which is not very commonly seen, and cyclohexyl. Alphabetized, we're going by the first letter in these. And tert, remember how tert actually is kind of like saying tertiary? That's why this one's alphabetized by B, and that's the I. And same here, B and then I. And C for cyclohexyl, and then I. But these are common names. This is not a hard rule. So if you find that in the book where they're out of order, don't be surprised. Sometimes people think it sounds better to say it one way or the other, so they just say it that way. So the alphabetic order on common names is not a hard rule. All right, systematic names are a little bit easier to stomach because we're only going to do one little thing. We're going to name it as if it's the prefix based on the carbons. So meth or methyl, and then we're going to put oxy on there. So turns out the ethers will never actually change the backbone. We're actually always going to call the oxygen and the smaller part of the ether a substituent. So even though I got this thing right here, and you might see it actually written to look something like where they're drawing attention to the O, and then we just branch up here and do these other 2 carbons. And that looks like an ether. But when we name ethers, the ether never takes priority over the backbone. So the ether, the smaller chain, will always be a substituent. And we will name it, since that has 1 carbon, a methoxy. All right, and that's where these things come from. So we would just immediately find the oxygen and take the smaller side and turn that into a substituent. and then we want to build the molecule or the backbone, so that's one of our substituents. I'd make that the carbon 1, 2, 3. So we have an ethoxy and a methyl coming off of a pentane. And this one is longer, but we do want to check it. 1, 2, 3, 4 carbons on this side. 1, 2, 3, 4, 5 carbons on this side. And even if these were the same, we'd want to go with the right side as the backbone because there's other substituents off of it. So typically we try to get the more complex side to be the backbone. And this would have to be the 1 position because it has a functional group coming off of it, 2 and 3. So we have methyls and methyls, and this is a butoxy. So 1 butoxy, 2, 3 dimethyl pentane. And this is a weird one. The O in the simple side must be a substituent, so these are both isopropoxy, because this is isopropyl, isopropoxy. And then there's a butane in the middle, because the butane is the backbone. Just one's at the 1 position, one's at the 4. Alright, next functional group we're looking at is alcohols. Now these will define the backbone a lot more, as in the sense that anytime you have an alcohol, the last name or the suffix of the chemical is going to have the OL or OL suffix added. Alright, but first we're going to talk about primary, secondary, tertiary. This is very similar to how we decide if it's primary, secondary, tertiary on an alkyl halide. You will find the OH, you'll look at the carbon it's attached to. If that carbon is attached to just one other carbon, you have primary. If it's attached to 2, secondary. If it's attached to 3, tertiary. And these will definitely behave differently on our chemical reactions. Sometimes they react faster in our chemical reactions, and sometimes they're slower. And we will definitely be covering that later in this semester. The reactions, that is. All right. Common names, very similar rule to our alkyl halides. We can treat the R group attached to an OH as a substituent, and since that's an ethyl alcohol, propyl alcohol, isopropyl alcohol, isobutyl alcohol. You're naming the substituent and then what it's attached to, the alcohol. But those are common names. IUPAC name, we're going to end up changing the suffix to OL. OL. Now, there's no number here because both these, it would actually have to be the 1 carbon. So since there's no choice, we always put the, we don't bother to number it. But if I were to do 3 carbons in a row, and I'm going to do the carbons, I could put the OH on the end, or I could put it in the middle. And technically all we're going to do, call that our backbone. Say this is off the first one, so this is 1 propanol. And this is 2 propanol. We're just going to number the backbone to say where it is. Alright, something nice that we're going to add to it though. When you actually have more than 1 substituent, we're going to simplify our rules when there's an alcohol involved. So I'm boxing in my entire backbone. Alright, but the nice thing about having an OH in there, the alcohol is the higher priority functional group of anything up there because they have more priority than anything we've talked about so far. So we want the alcohol to have the lowest possible number, and we don't care about anything else. So I'm going to make this the 1 position because that's where the OH is. The OH is here, so I'll make this the 1 position. And the OH is here, so this becomes the 1 position. So it overrides how we go about numbering it. You always want the OH to have the lowest possible number. Even on our rings, which we're going to see now, or next, the rings will actually always have the OH at the number 1 position. Alright, now something weird that happens on this, on the IUPAC name. When we actually have an alcohol in it and we need to number it, we can put the number 1 of 2 places. So both the names down below are actually saying the same thing. They have the alcohol at that 1 position, have this methyl at the 3 position. This one has the alcohol at the 3 position, no matter how we count it. But what we can do is we can call it 3-pentanol, because we're saying that the alcohol part is on the 3rd position, And here we're saying 3-methyl-1-hexanol, because it's saying there's a methyl at the third position, and the alcohol is at the 1. But what we also find is you will sometimes see the number embedded in the suffix, and it's right before the suffix that it's in question of. So pentane 3-ol, the 3 is telling you that the alcohol is on the third position. And same here. So the number being embedded in the name is perfectly acceptable, and it does get more common when there's more than one functional group present in a backbone, which we'll see here in just later on in this chapter. All right, diols are a thing that happen, and that's all we do is we add the di prefix before the alcohol. So we have our nice long backbone, but we have 2 alcohols. And all we're going to do is number where they're both at and put a di in front of the prefix. And technically there are triols and so forth and so on. You do have to tell the reader, or when you name it, that there is more than one OH in that backbone. Alright, excuse me. This is just more of a summary of it, but we're just wanting to stress out that the backbone doesn't necessarily have to be the longest continuous chain anymore. What I mean by that, well, this one doesn't really affect it, but on this one, this carbon here is actually the longest possible chain. It would be actually 6 carbons, but that doesn't actually have the OH as part of it, and because of that, it can't be the backbone. On this particular structure, that carbon must be part of the backbone because it has the OH attached. Now, making it the longest group was easy enough to go across here, but what we're seeing is since the functional group must be part of the backbone, you will change which is the longest chain. Like even on this ether, when we first introduced ethers, we said to find the shorter chain and make that a substituent. Well, we don't now, because on this particular compound, there's an OH. That takes priority, so this over here must be the backbone. So we went from having a butane to a propane, just because we have these nice little rules in place. Becomes a substituent, which is why we have a propanol with the OH at a 1 position and a butoxy at the 3 position. Alright, other weird things that pop up. When there is a tie, which is what happens here, we could go 1, 2, 3 and get to that OH, or 1, 2, 3 and get to that OH. Doesn't matter which direction, so since it doesn't matter, we look at the next possible substituent, so this must be the 2 position. And that happened here as well. It doesn't matter which direction I go, it's 1, 2, 3, 4, or it's 1, 2, 3, 4. So since the 4 is where the alcohol is directly, no matter how I number it, we're going to go over here to make this have the lower possible number. And the last weird name that pops up with alcohols. If I have a ring, the alcohol is definitely on the 1 position. Or that high priority functional group will be at the 1 position. So since that's at the 1 position, this methyl must be at the 3 position. And the other thing that's going to pop up, when we name it, we won't bother to put that 1 in there. Because since it is a cyclohexanol, it's assumed that that's at the 1 position. So you will number all the other ones, but not the alcohol. And that even applies when we get more complex, like this one here in the middle. That alcohol is definitely at the 1 position. So 1, 2, 3, 4. You will number the methyls at the 3, 4 position, so 3, 4 dimethyl. And then you're just going to say cyclopentanol without numbering the cyclopentanol part. And even over here, this must be the 1 position because it's the alcohol. So number the rest to get the lowest possible numbers. 1, 2, 3, 4, 5 is much better than 1, 2, 3, 4, 5, 6. And then we just follow the rules. Ethyl comes alphabetically before methyl, so 2-ethyl, 5-methyl, cyclohexanol without a number. But over here, I have to number it because that OH is part of a continuous chain, and it's very important to say where it is. So this one is definitely at the 2 position, 3 ethyls at the 4 position, and bromine to the 7 position. Okay, next functional group we're going to look at are our amines. Now our amines are just something that has a nitrogen attached to a carbon chain. And there are primary, secondary, and tertiary here, but we figure out if they're primary and secondary, tertiary, totally different. On the alcohols and the alkyl halides, we talked about the carbon that was directly connected to those. On the amines, it's the carbons directly attached to the nitrogen. So if the nitrogen's only connected to 1 carbon, it's primary. If it's connected to 2, it's secondary. And if it's connected to 3, it's tertiary. Now these actually end up with sometimes a lot more vary in their even their physical properties. But you might be able to predict that even from understanding from introchem, because NH found on your primary and secondary bonds actually can contribute to hydrogen bonding and strong intermolecular forces. But here on a tertiary amine, there won't be any guarantee of hydrogen bonds. They'd have to come from whatever else is attached, but it's not from the nitrogen. So they do get some different chemical properties and different physical properties. All right. That's just showing our summary of how we decide primary, secondary, tertiary. Because it's interesting, this always gets some confusion. A primary amine only cares about what it's attached to, not all these things that are connected to that carbon. All right. Common names of amines, we kind of do the same thing. We just treat the things attached to the nitrogen as a substituent, and then say the word amine. Now the difference here is the ethers and the alcohols, you saw spaces in there. So if it was CH3OH, it was methyl space alcohol, and CH3Cl was methyl space chloride. But amines, there are no spaces. It's all one word. But it's still doing the exact same thing. We're going to name the substituents and then put the word amine, and we typically list the substituents in alphabetical order. And if there is more than one of the exact same thing, like this one, we do see dis, and sometimes even tris, which is what happened down here. But those are common names. IUPAC is just ever so slightly different. What we're going to do is take the longest potential chain off of that nitrogen and make it the backbone. It's like over here, that's easy to do because there's only, since being a primary amine, there's just a single continuous carbon chain off the nitrogen. So since that's butane, this becomes 1-butanamine or butan-1-amine. On my second one here, I have a secondary amine because I have that carbon here and I have this carbon here. My more complex carbon, or the longer carbon chain, becomes the backbone. So the backbone tells us this is a hexane amine, and we will put the amine at the 3rd position. But we have to do something about that substituent. And it's not coming off the backbone, it's coming off the nitrogen. So what we're going to do to stress it's coming off the nitrogen is use the letter N, typically in italics. So N-ethyl 3-hexanamine. And that happened here. So I had a propyl group, I had an ethyl group, and I had a methyl group. Since the propyl is the longer or more complex chain, it becomes the backbone, making it a propylamine. And then we have an ethyl and a methyl coming off of the backbone. N-ethyl, N-methyl, 1-propanamine. Alright, something else that can happen. So our N is just an indicator. So typically we find it listed alphabetically when we do a name. So we find our long chain of the backbone. That means this guy and this guy are substituents. We have a methyl and a chloro. Alphabetically, chloro comes first. So 3-chloro, N-methyl, 1-butanamide. Similar thing happened here. Backbone with an ethyl and a methyl. Ethyl comes first, so N-ethyl, 5-methyl, 3-hexanamine. And even on this last one, long backbone, going to get the amine to have the higher, amine being the higher priority functional group, gets the lowest possible number. So it's the 2, therefore the bromine's the 4. So we have a 4-bromo pentanamide, but what we're going to do is alphabetically list these. Bromos come before these methyls. So 4-bromo, N-N-dimethyl, 2-pentanamide. And that even happens on our ring. So this is definitely a substituent on a ring. That's definitely a substituent of the ring. But this is going to be the 1 position. But since the amine takes priority in the functional group, we don't number it on the ring. So the only ring number is the ethyl. So 2-ethyl, and then N-propyl cyclohexanamine. Oh wait, got one more thing I wanted to have on here. What we're going to do is I'm going to take this slightly more simple molecule, CH3, CH, CH2, CH2, and then NH, CH3, and a CH3 down here instead. So still have that same exact backbone, but now we have 2 exactly the same substituents. All right, this is a weird one. So it is methyl, and typically, and your book is really good about doing this, we would see N, 3 dimethyl, and then still has the 1-butanamide. But what we're going to see as well in the literature is they will separate these out. And what I mean by separating them out, we'd see N-methyl, 3-methyl, 1-butanamide. And you're going to see both. But technically, when there's ties like that, we should have the N first, N and then 3. We actually see kind of both still in literature. Now, the modern rules do have us say put the N first, and that's how we're going to have it on our tests. All right, last one we're going to talk about is the ammonium salts. Now, these are quaternary amines. Quaternary meaning that particular nitrogen has 4 R groups coming off of it. The only way that happens is if we protonate the nitrogen. This will drastically change the chemical's properties because as a ammonium salt, it becomes ionic in its bonds. So, and these have all the benefits of ionic bonds. I mean, huge boiling points and melting points. They are going to be solids at room temperature. And they are, for the most part, soluble in water always, because all ammonium salts, the NH4 part, or the N plus part, is kind of like NH4, which was one of those substances in Chem 1 we said was always soluble. And these pretty much are very, very soluble. But when we actually name these, they're always named as if they are common names. So what I mean by that, we will name each one of these substituents and then say what they're attached to. Now, what we do find in some cases, we will find the IUPAC name of the tertiary ammonium salt, and then they actually add the phrase HCl at the end, which is really, really weird. So you'd have a long IUPAC name, and then they just do something like HCl at the end, and that tells you they've made an ammonium salt out of it. All right, but we're going to cover that particular naming when we get to the amines, so you don't have to worry about that yet, which I'm going to make it go away. Matter of fact, even the IUPAC naming of ammonium salts, they are going to be relatively simple ones, because I will need you to be able to identify all these as simple substituents. So ethyl, dimethyl, and propyl. So you can come up with those names. All right, so summary of our nomenclature. We haven't done everything, and we will be adding to this as the semester goes on, because we don't have any carboxylic acids in here. We haven't really done anything with multiple bonds, double bonds, and triple bonds. So we will be adding to the nomenclature. But fortunately, we don't add to the rules anymore. That whole idea that we change the numbering on alcohols and amines, we're just going to expand that to order. What do we do if we have an alcohol and an amine? So which one takes priority between those two? And we're not doing that quite yet. All right. Let's go on to some of the physical structures here now. So physical structures, more of the ideas how these things are put together, bond links and whatnot, and also bond angles. All right, so an alkyl halide, for instance, we're going to have longer and shorter bonds based on fluorine and iodine, the physical sizes of them. The smaller fluorine is going to be to get much closer to the carbon than the iodine is. That's going to drastically affect some of the properties. Mainly, it makes that bond weaker. So we're going to find that there are certain reactions that are very, very fast with iodine because of the weak bond, and we'll find some that are very slow with iodine for the exact same reason. So the strength of the bond is going to affect chemical reactions. All right. Now, when we look at other ones, we're going to actually focus a lot more on where the electrons are together. Now, weird thing is, we like to see pictures like this alcohol where they're showing those two electron pairs in little separate orbs. Well, what's weird is, it doesn't seem like it reacts as if there's a collection of electrons here and a collection of electrons here. It actually reacts as if all four of those electrons are kind of averaged between. Which is why we often do these electrostatic potential maps, because they kind of show that electron density, or where that reaction is likely to go. And this one even shows that slightly positive nature of that hydrogen, which is this being an alcohol, is going to have that pKa in the 15s, and that's why we're seeing that blue there. That H will come off a heck of a lot easier than any of those other H's in that particular structure. All right, but that electron density change, those lone pairs, are going to drastically affect the reactivity of alcohols compared to other functional groups. Same with ether. Ether has the same idea with those electrons there, and it does actually do the exact same thing, where the electrons kind of collect totally opposite of, or maybe an average between where those two are, and on our electrostatic potential maps we see the big huge red. Now, even though the O is the exact same thing as we see as alcohol, they typically don't react quite as well, and that's simply because this is not a hydrogen. So that being both carbons, they're actually in the way. They're also pulling the electrons away from the oxygen some, so it's not nearly as negatively charged, or not nearly as, we're going to say, reactive towards positive structures. So it will adjust the reactivity. All right, amines drastically affect the reactivity based on what's attached to the nitrogen. Now, what I mean by that remember how we introduced primary and secondary or tertiary? Those other carbons will make that electrostatic red area slightly less available because they're blocking that reactivity. All right, but what we're seeing here is the structures are very important. Now, the structures here are Chem 1 type of ideas, as in it is tetrahedrals and trigonal pyramidal, so there's nothing new per se, but we do want to get comfortable with doing it quick just by looking at a Lewis structure and see, hey, methylamines, primary amine, sp3, easy to get to it, that lone pair is very accessible. All right, but that's why we're doing this. Even the electrostatic potentials, if you actually are in the lab and have looked into Avogadro, you know you could generate all these pictures yourself if you wanted to do it with any other molecule. It's actually a very straightforward, cool little program that does that. All right, let's talk about some physical properties. Boiling points are something we actually talk about a lot on our classes of compounds. What I mean by classes, we will relate the boiling points of our alkanes, which are just those hydrocarbons, to alcohols, which I can do the exact same formula and add just an O. But that particular molecular formula could even be an ether. But we know, even from general chemistry, that where that O goes in will drastically affect the intermolecular forces, because I could put two carbons on either side of the O. There's no possible way that this thing has hydrogen bonds, so it's just a dipole molecule. It's a polar molecule. It's going to have a much higher boiling point than any ether would, or any ethane would, but it's not as high as it could be. especially on the way to put these together, because I could also put the oxygen on an end. Put the carbon in the middle here, and if the oxygen's on the end with an H, we've created a hydrogen bond. So drastically different boiling points just based on that. So we are going to review and back up and talk about our inland molecular forces and add to it. Because a general issue we have with organic molecules is there really isn't a single force in many cases. Because while this ethanol can do hydrogen bonds, this part of the molecule here, being nothing but carbons and hydrogens, is going to actually do more van der Waals. And it gets to be a big problem if I go to long chains of carbon and then add an OH. Because it turns out while this one is aqueous and dissolves in water very easily, in almost any ratio, this one pretty much doesn't. I'm going to put it as a liquid. It will actually stay slightly separated. It doesn't mix very well. And it's mainly because that chain is too long for the water to fully go around it. Now it still has hydrogen bonds. It still has a wicked high boiling point. It just actually can't hydrogen bond with water well enough to dissolve. Okay, so if I keep it simple and look at just my alkanes, just carbons and hydrogens, we actually can predict what the boiling point and melting point is just by looking at the number of carbons. I see that I'm missing something. That should have a negative in front of it. But the boiling point just steadily goes up, and it's a very predictable number. And we actually can, if we were to actually get into a program like Avogadro and calculate the surface area of the molecule, we could see that these boiling points is almost directly proportional to the surface area of the molecule itself. That surface area plays in because if I take the exact same carbon chain but start ripping things off and moving around, so what we did here is we took this carbon off and we put it on that second position, and then to go here we took this carbon off and also put it on the second position. Well, that actually decreased the surface area. It added more branches to our backbone, and as we branch up our backbone, our boiling points drop. Lower surface area. Alright, dipole moments are actually easy to predict on all of our organic compounds. And we almost can say this: if you know a molecule has a particular functional group, that functional group will give a dipole moment. What I mean by that, or in other ways, all of our alkyl halides, simply because there's a halogen there, are going to give a polar bond and actually end up giving the molecule dipole-dipole interactions. Now, carbon and chlorine are close on electronegativity, but it's still far enough apart that it can create a polar attraction. And same thing happens with oxygens and nitrogens. Just having the lone pair of electrons on the oxygen creates a dipole moment, and we see a drastic increase of boiling point just by adding an oxygen into the same type of structure. And it is just because it creates the possibility of a dipole-dipole interaction. And what we have here is just comparing different classes. Now, we do this because we generally find this trend applies, in the sense that alkanes pretty much always have the lowest boiling points for their molecular weight, and alcohols are some of the highest. Now, I say some of the highest. Highest are actually carboxylic acids, which have the RCOOH, and we haven't introduced those quite yet, but those typically have higher boiling points based on their molecular weight. And amines vary, but the biggest reason amines vary is both of these are primary amines, but as soon as you have a tertiary amine, you no longer have an NH bond, and your boiling point will drop tremendously. So it's not fair to say that amines are always going to have higher or lower boiling points than any other group, because they move around some. Alright, now this is a neat little thing when we actually look at the effect of a halogen, because it has a very predictable behavior. We really actually can relate boiling points to the length of the carbon chain and the molecular weight of the halogen, in the sense that the heaviest ones, iodine, always end up with the highest boiling point, and fluorine always ends up with the lowest boiling point. So this is almost directly comparable to the molecular weights that you would find for each one of these individual molecules, in the sense that if you had the molecular weight of any one of them, you could compare it to their boiling points. They'd be the exact same order. All right. Now, the last little thing we want to remind you on is hydrogen bonds. Now, hydrogen bonds are very, very versatile to explain boiling points. They also help a lot of times to explain solubility, but it's not perfect anymore. In the past, especially Chem 1, if you had something that could hydrogen bond to itself, it was likely to say it's soluble in water. It's not the case anymore. We need smaller molecules, and we need less London dispersion in the molecules. As soon as I add too many R groups, we actually start getting some interesting things. But we will see this also greatly affect some of our chemical properties and our testing abilities. So hydrogen bonds are going to be a common thing. But keep in mind, for a hydrogen bond to occur, you need an OH somewhere in the molecule, an OH bond, an NH bond somewhere in the molecule, or an FH. Nothing else will actually create hydrogen bonds. You need one of those three bonds somewhere in the molecule. But if they're there, they will hydrogen bond with each other, as in molecule A with molecule B of that same type, which is what we're showing on this page. Up here is a bunch of water molecules, hydrogen bonding. Here's a bunch of ammonias, hydrogen bonding. Here's a bunch of hydrogen fluorides, hydrogen bonding. All right, and, well, that doesn't need to be shown. All right, hydrogen bonds and amines are the variable. So hydrogen bonds and amine, you need an NH. And since you can build the same exact chemical structure with no NH bonds, we will see a drastic change in boiling points just by not having an NH. So tertiary amines never actually form hydrogen bonds, but primary and secondaries do. Okay, next little thing we'll see is that biologically speaking, we will find that chemicals with similar structure and shape typically behave slightly similar in the body or have similar effects, which is what happens here with salicylic acid and acetylsalicylic acid. So salicylic acid, which medically speaking now, it's pretty much only used as the active ingredient of acne cream, because it opens up the blood vessels and gets the blood flowing. That gets the bacteria and such that cause acne to get killed or attacked by the red blood cells. Theoretically, you could actually take that active ingredient, the salicylic acid, and use it for headaches. The reason you wouldn't want to is this particular carboxylic acid and that particular OH make this kind of acidic. And it's a little bit too acidic for us to consume in major amounts. I mean, I guess if you were a 1 aspirin every year, salicylic acid would have a similar effect and work fine, which is why Native Americans chewed on certain tree bark. And it was something that even the Europeans did, because there are trees that are out there that actually have enough salicylic acid in them that the tree bark itself could actually help cure a headache. But Bayer figured out that if you neutralize that OH, make it less acidic, you have something that works very similar to salicylic acid, even better in some cases, but it's no longer acidic. And then Tylenol actually takes that one step further and makes it even less acidic by actually totally removing that OH. It does have to put an alcohol in there, which is acidic in itself, but this Tylenol, acetaminophen, is not anywhere nearly as acidic. Okay, other weird thing that pops up. Turns out melting points, which do increase the same rate as boiling points, have other factors involved with them, which is why they don't perfectly go up always the same rate or the same amount as boiling points. Like our straight chain alkanes, we will see this weird little zigzag pattern, and that's what they're showing here. So we're going up by the number of carbons. 1 carbon, 2 carbon, 3 carbon, 4 carbon, and you see kind of a zigzag going. The odd numbers, when there's an odd number of carbons, you have a bigger jump, and when there's an even number, there's not much of a jump. Weird, huh? Alright, reason that is, turns out when a solid is formed, how you pack the compounds is darn important. You need to actually be able to fill up a certain amount of space very well organized. And there is a different lattice energy or a different packing stability in odd versus even. So technically speaking, we can say the odd number carbons pack less tightly. What ends up happening is, think about being a continuous zigzag here, there might be an empty spot there. So those empty spots are where a carbon could go actually hurt the efficiency of the packing or make it less tight, and that affects the boiling points or the melting points on these. All right, solubility. I've been alluding to this a lot, and we used to use this term like dissolves like, and that still applies. But I want you to view like dissolves like as not necessarily unique for an entire molecule, as in small molecules have very particular and very specific intermolecular forces. Water, it's totally dominated by hydrogen bonding. But as soon as I take that OH and put it with a longer substance, blah, 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 don't even matter what it is, the other part of the molecule has different intermolecular forces that might control it. So it might not be safe to say that molecule is dominated by just hydrogen bonds anymore. So while we will use like dissolves like, we have to actually focus a bit on the gray area of what the rest of the molecule does. And we will use terms like solvation to describe this. Now, the reason we use that is there are, generally speaking, certain organic compounds that are always soluble in things like ether, and there's certain ones that are always soluble in, say, water. It is related to other factors. Now, what's weird is the other factors are what ether we're talking about, because I did say ether like that on purpose, because ether is just something with an O surrounded by R groups. It's going to have a dipole-dipole interaction. But if my R groups are large enough, this is also going to have some London dispersion forces going on, which is why ethers can dissolve many organic compounds, because organic compounds are polar and nonpolar. But the right ether, or the right ether for the situation, might dissolve all the organic compounds you need. Yet, not many will be fully soluble in water. So when we actually talk about solvation, we talk about classes of compound. We will compare it to which solvents or which type of solvents are best to create solvation. And we will also find out that the solvation, or what your reactants is dissolved in, will drastically change chemical reactivities. Alright, so this is what I'm going to talk about with regard to solubility of ether and water with various different ethers. Now, when I have small molecules, so small substituents, and I mix it with water, I see that the dipole-dipole interactions that the ethers have with themselves is comparable to the hydrogen bonds found in two water molecules. And since they're comparable, these will actually mix. They will be soluble in each other. And even if I take it up to 2 carbons on one side, it's still soluble. But as soon as I get slightly longer, 2 carbons on both sides, I start to see the solubility drop drastically. And we get a general rule of thumb for many organic compounds. Once you've got to 6 carbons, it almost doesn't matter what else we put onto it. Once it's up to 6 carbons, it's pretty much not going to be soluble in water any longer, or it's going to be drastically reduced in solubility. Now, alkyl halides, we're not going to find much solubility at all in water. And that really is because the dipole moment's simply not ever going to be high enough to get a true dipole-dipole interaction. But some of them are. So the more polar the bond is, the more soluble it will be. So that's why the fluorine-containing compounds are actually found to be soluble in some cases, because fluorine, being super electronegative, has made a very strong dipole-dipole interaction. And it's strong enough that that's compatible with water. But as soon as I get too many carbons on there, I lose that totally. So we're talking 2 carbons is all to stay soluble, and then we're just slightly soluble with 3 carbons. And we kind of see that same thing with chlorine, but we're actually really only soluble with one carbon. And then bromine and iodine, never soluble in water. All right, last little thing we're going to talk about, and it's opening up a lot, so there's a lot of page to cover this, is what happens when a single bond rotates. Because obviously they do, because the overlap that forms a sigma bond is just the overlap of p orbitals. And back in general chemistry, we said those sigma bonds were just the overlap between those. Well, this thing could rotate one way, this could rotate the other way, and it'd still look the same. All right, so that really happens in a molecule. They actually rotate. And we're going to care about that. Now, I have this picture here. I want to show you what it talks about. I'm going to switch over to Avogadro. Remember that wonderful program? All right, so I have that same molecule here. And let me rotate it so we can see what we're talking about. So it is just ethane. It's got 6 carbons. And right now I got this distance here. I actually tagged these 2 carbons. I want to show you something. Because what they're talking about on the rotation of bond, if you notice right now if I rotate this, it almost looks like these carbons are like 60 degrees away from each other. All of them. They're actually rotated. Well, this bond in the middle can rotate. So let's see what happens if I were to rotate it. All right, theoretically, I can just click right there. And, oh, it's not rotating. There it goes. Nope, I'm just rotating one thing. And that's not rotating it. Get this closer to me. See, I want to click, yeah, there we go. And, there we go. Alright, now what I'm going to do here, because this mouse is just, I don't have the best mouse. You look down that lower corner, the distance is getting smaller and smaller. I'm going to get it as low as I possibly can. Because you notice it's going to get to a point and then it's going to start going back up. Yeah. So it looks like 2.403 is about as low as it can be. Now, reason it's low, if I rotate this again, technically now, those carbons are hiding behind each other. All 3 of them. Alright, so it's eclipsed. That distance is closer. That is, those hydrogens being hydrogens, they're trying to repel each other. They're trying to want to get as far away from each other as possible. Matter of fact, if I tell Avogadro to optimize the structure, it rotates right back to where they're close to that 2.5. They get as far away from each other. Well, what we're going to see is in our chemical world, that's a way for a molecule to absorb energy. And it's not really all that much energy difference. That was only about 12 kilojoules of difference, or about 3 food calories for it to sit there and spin on its own. And we have this neat thing. Since it happens enough and we care about it, and it's an explanation of what goes on with energy, we name these 2 structures. And what we're seeing here, this is, we call it a Newman projection. And Newman was just the guy that said, all right, we're going to say that circle there is the first carbon, and technically another carbon's directly behind it, hidden by it. And these 3 bold lines are the 3 other things coming off that carbon, and the 3 back are the ones going backwards. So this staggered really is the same thing we were seeing on Avogadro. It's that staggered. These front 3 are coming off the first carbon, these other ones are coming off the back. It's just a different way of looking at ethane. And back on here, that is a different way of looking at it where they're hidden behind it. Now, to keep the name simple, this is nice. How about I spell that right? Eclipsed. Staggered. I have no idea what I'm writing there. Looked like an A, and there was only one G. But staggered and eclipsed. Now, it is just a 60-degree rotation. It's just a small amount of energy, but we call these two things conformers. Now, a conformer is just a different way of rotating the bonds. It's the exact same chemical. Your book has a picture to actually explain conformers later on. You're going to see a picture of a dog, because technically a dog, no matter how they lay around, there's 4 legs, and you can tell a difference between a front leg and a back leg, and there's a tail. And if you were to somehow swap one for the other in, say, a picture, it wouldn't look right anymore. And that's what a conformer is. It is ethane. No matter how I do it, it's just a different way of looking at it based on those bond rotations. All right. But this whole idea of that staggered and eclipsed, what we're seeing is it actually adds some strain to the molecule when they line up. Now, they use this word hyperconjugation. I don't want to focus on this yet. We're going to focus on that type of stuff a little bit later when we start doing bonds. Right now, I just want you to realize that these hydrogens want to be as far away from each other as possible, which is why that bond rotates. And it even does the same thing along a longer and more complex molecule, like butane, which is what we have here. Now, we're doing the same type of thing on the Newman projection here. So let's go over to Avogadro and make butane so we can see what they're doing on these pictures. So I'm just going to go here to my drawing, click here, and just real quick, I'm going to tell this to optimize the structure, because I know Avogadro's going to technically, even if I don't have it oriented the same, it's definitely the same thing as this, because that zigzag pattern is always the lowest energy. And going back to Avogadro, we can actually rotate this and see it. So what I'm going to do my rotation, if you look down, those 2 carbons, everything's staggered. Staggered, 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 staggered. And then if I rotate it and look at the 2 and 3 position, let me move this into page. I think that, yeah, that I don't want to do that. Yeah, okay, so staggered. And then if I rotate it to look at the 3 and 4 position, the very last 2, it's also staggered. So we see staggered all around. And the more interesting one to look at is this middle position. So right along here. Because what we see there on this staggered thing is these 2 big groups are as far away from each other as possible. All right. On our books form, what we're pointing out is that goes on. And that's what they were showing on the carbon 1 and 2, and then carbon 3 and 4. But I want to focus next on what goes on between 3 and 4, because right now these guys are far away, but they could be closer. So that gives us a lot of conformers. What I mean by that, we could have those carbons where they're fully eclipsed with each other. Rotate it a little bit, we're back to a staggered form, but these methyls are still close. And we go to an eclipsed again, but it's no longer eclipsed with a methyl and a methyl, and then we finally fully cross in another staggered form. Well, and that's what we're seeing here. Matter of fact, something that's kind of neat that Avogadro will do. Under the Molecular Mechanics tab, there is a button called Conformer Search. Now, it won't find all of our conformers, but I'm going to hit this so you can see what it's doing. See how it's just rotating that 2 and 3 bond that we were looking at? What it's doing is it's trying to find where we have the most angle strain, and more importantly, where we have the least. I shouldn't have done 100 trials, but it's going to be done here in just a second. And it will just stop, and you won't see anything at all. And I'll have to go in there and, yeah, so it just stopped. Now, technically, it did do one of the staggered, but if you notice, these 2 methyl groups, the 1 and 4 position, are now closer. But now if I go here to properties and conformers, I get these different numbers, and if I click on it, it will actually rotate. Now, it's not going to find all my conformers. And what I mean by all my conformers, if I go back to my slide, it found just the low energy ones. It found them where they were totally staggered, which we actually call anti, and where they're still staggered, but the methyls are actually closer, We call this gauche. But Avogadro doesn't find the maximums, the high points. It only finds the minimums of them. And yet these are important positions because really, if you think about it, to get from gauche to anti, it has to go through this thing. It has to actually put some energy into it. All right, so this particular structure is just called eclipsed. And the difference between this eclipse and this eclipse has both those methyls overlapping with each other, so we call it total eclipse. Alright, but that bond, even though all single bonds can freely rotate, there is some restrictions to this. It does actually take some energy to do a full rotation. Now, it's not much. If we have butane, even butane from like a little, one of those little cigarette lighters, just the sunlight is putting enough energy into butane to get it to fully rotate. It's not having any difficulty at all at absorbing and giving off that energy with this rotation. Alright. But we're going to see that because that straight chain molecule will have the lowest energy where every other carbon is far away from each other, we see the zigzags used all the time. And that's why we've been drawing them with zigzags, because that's always that low energy conformers, to have all of it drawn out zigzag pattern and get it as long as possible. Alright, there is some limitations. If I make a ring, I'm going to potentially limit the bond angles. Now, reason I say potentially? Alright, so a triangle, bond angles must be 60 degrees, square 90 degrees, pentagon, hexagon. They are limited by their degrees geometrically speaking. Fortunately for the real world, we don't have to be planar. So these are the angles as if the shapes were fully flat. Well, it turns out in the chemical world, they don't have to be planar. Or even in the geometrical world, they don't have to be planar. Now, 3 points do, because 3 points define a plane. So, cyclopropane is definitely perfectly symmetric, pretty looking. These hydrogens are fully eclipsed, so there's a tremendous amount of bond strain. This bond angle is definitely 60, even though it'd rather be 109. So we have a lot of angle strain. It makes a molecule like cyclopropane relatively unstable. It's going to react chemically very quickly to open up that ring or relieve that ring strain. We have something similar happens to cyclobutane. But can you see on this picture how it kind of looks like maybe these two carbons are higher on that plane than these two? Well, what's happened is we've actually ever so slightly twisted the ring to get the hydrogens ever so slightly further away from each other. And by getting them slightly further away, that strain is less, but it does actually change these bond angles. These angles are closer to like 89 degrees. So they're tighter in the angles, but the hydrogens are further away. Now once we get to cyclopentane, they're no longer confined to be a plane. It's still not perfect. It's got a lot of strain, but they're out of that restrictive plane, so we don't have those 105 degree bond angles that a pentagon would. And we totally get away from it with cyclohexane. Look at this. Cyclohexane fully does a ring, and it actually zigzags. It goes up and down all the way around. Matter of fact, all these bond angles are sitting right at 111 degrees. Not even anywhere close to the 120 that you get on a square. But that up-down part, that zigzag, really gives a reduction in strain. And what we're showing here is the Newman projection of that. So you can see that one carbon on the end is higher than the other. We're getting a weird, they call it a chair form. So that's like the foot of the chair. Here's the back, and up here's the back of the chair. Okay, now bond strain itself, or to compare what that bond strain is doing to the molecules, we're looking at these. And the more important one to notice, cyclohexane is almost as stable as if it was an open chain. So it's almost every bit as stable as, or it is as stable as hexane. The ring makes no difference to it. But cyclobutane, cyclopropane, cyclopentane, there is enough strain in them that it makes them more reactive than if they were a straight chain. Even the bigger rings are slightly more reactive, but they're not going to rip apart. So cycloheptane, cyclooctane, cyclononane, decane, and undecane, the bigger chains will get close to that zigzag pattern just because of that big space they have. And as long as we get to that zigzag pattern, close to the 109-degree bond angles, we have released that strain. We just can't do that with cyclopropane, butane, and pentane. Okay, but because cyclohexane is darn stable, we have to learn how to draw it differently. Because while I can draw this, and that's perfectly acceptable, it is sometimes important to talk about positions, because let's put a chlorine here and a chlorine here, one on either end of it. Because the molecule actually looks like a chair most of the time, where these two chlorines are is kind of important, because if I'm going to say this position is this position, I have two different locations I could put that chlorine. And this one, same here. So I could put both chlorines going out. We call those equatorial positions because they're going out from the ring. And I could put one out, and it turns out one straight up. Now, even though there's four positions, and it seems like there should be four possible ways of drawing that, there really are just those two. And we're going to see why in just a second. But these are totally different structures, even to the point where I would have to draw this as with wedges to indicate that these two chlorines are both going up on the ring, or one's going up and one's going down. It's darn important to draw it that way. And those two are totally different molecules. So we're going to have to learn how to draw our chairs, conformers, and put stuff on them. But to draw it is actually kind of easy. We are just drawing a weird looking, almost like a lightning bolt. And they do say chair because this looks like the old pool chairs, the recliner type things. And then when I draw the hydrogens on there, I'm going to do the hydrogens in a different color. And I will do the horizontal ones. There's three going over here to the left and three to the right. I just said those words backwards. But the horizontal ones are just even like that. The up and down ones alternate. So my going up, I'm going to have this one and this one and this one go up. So every other one. 1, 2, 3, 4, 5 go up, and the other three go down. Now we're going to do something weird. We're going to talk about positions. It turns out these going off to the side, we call these equatorial positions. Because on the ring, on a three-dimensional real drawing, the equatorial are these ones that are coming off like a ring. And the axial ones are the ones that go up or down. And your book has a better drawing of those because they used math and a graphics program to draw it. But they're showing the equatorial and axial. Now, the odd thing is, though, we're not restricted that equatorial is always equatorial and axial is always axial, because it turns out these rings will flip. And just think of it like a chair. So if we're talking about the patio chair, what's happening over time is we make the top end go up, or one of the ends go up, or one of the ends go down, and then we'll just bring down the other one. We call it a ring flip. Now, technically it's a conformer change. So I got a graph to show you the conformer change, because what's going to happen when it goes up, these hydrogens get closer, and along this 1 and 2 bond, and even the 4 and 5 bond, we would have eclipsed. So we had on the previous page the chair conformer. This is a boat conformer. See how it kind of looks like a boat now? Alright, but to get to it, we have a weird thing that happens. If you think about that whole mechanism I had that I'm kind of showing, this thing must come up, right, to get to this point? Well, at one point here, it would be perfectly flat. It'd have to be, right? Well, that trim requires a lot of energy. That half chair, where it's perfectly flat, requires a lot of energy to get to it. And then we go to the boat. But we don't go directly to the boat. We actually go to what we call a twist boat. And the point of the twist boat, let's go back and look at the boat. So since these hydrogens, we call them the flagpole hydrogens, are close, what we're going to do is kind of think about pushing one into the paper, pulling one out at you. And what would happen is this side, if I pull this one towards me, the 1 goes down, and if I push that one up, the 2 goes up. So this would be the 1 and 2. Then we'd still be connected to where that 3 position is, and this hydrogen is now into the paper. But this one, hydrogen's coming towards us. But we've actually caused a bit of a twist to our backbone. We've twisted the boat. Now, better way to draw the twist boat, to be honest, rather than try to explain what I'm doing there, I'm actually going to draw the twist boat with an X. And the reason I'm doing that is I'm going to come up here and now I didn't get that up high enough. I needed to do that leg first. Because this twist to it, these are that's an intersection, that's an intersection. That twist to it has got these hydrogens slightly further away from each other. Just slightly, but that's relaxed it some. Alright, but that's our full change. We go from chair to the half chair to the twist boat, which there's a reason it's not drawn. I'm never going to ask you to draw any of these, to a boat, and then back to a half chair and chair. But we're going to actually focus on the fact that we can go from chair to chair, not so much how it goes from the two. Alright, but when that ring flip happens, something interesting happens. An equatorial position always becomes an axial position. So if I have a methyl group, per se, off that ring, there's a chance it could be equatorial, and it could go through a ring flip and be axial, because they always alternate. But that happens always. So if I put another one on here, another methyl that is, and made it equatorial on the other chair, it would also be axial. So when a chair flip happens, that's not the picture I wanted. I don't even have it. Alright. Oh, I know where it was. I know what I'm looking for. This thing. When a chair flip happens, the axial positions and the equatorial positions, all of them swap. If it was axial, it becomes equatorial. If it was equatorial, it becomes axial. Alright, so that's what happens on this. So they swap. I can't erase my ink. But when we have something like this, where there is a single methyl that's equatorial or axial, we will find the ring flip favors the side that keeps as many groups as possible equatorial. So in this case, we have a conformer that's more stable than the other, more stable chair conformer. And we see that's happened mainly because you don't want that carbon group as close to hydrogens as it would be if it's equatorial. These are physically too close. That creates strain, and it's easier for the chair to flip to the other one and keep it out on the equator, the equatorial position. All right. We can see that also is going to factor in with the hydrogens on that group, because if that particular methyl group has hydrogens, they're also going to be repelled. So there's just actually repulsion going on, which is going to help keep that particular chair in the other conformer where that methyl is equatorial. All right, and yeah, that's not really anything interesting. This is, though, whatever that substituent off the ring drastically affects the stability of one chair over the other. And this is probably the more interesting one. 4,800 times more likely to be equatorial versus axial if that substituent is a tert-butyl group. So if I have a ring, and on this ring I add a CH3, so a tert-butyl group, I know that pretty much the only chair conformer that one's going to form is going to have that thing equatorial. And that particular structure pretty much is not going to go through a ring flip, because it's 4,800 times more likely to be like that than it is to have it in the equatorial position. Now the other one's not nearly as much. It has a lot to do with the bulkiness. So typically we find the most bulky, the largest physically, substituent wants to be equatorial. Everything else would actually be okay with axial in that case. Alright, but sometimes it doesn't make a difference. What I mean by that, these are the two different ways we were drawing that dimethyl cyclohexane. One has both of them going down with respect to their positions. So we would draw this where they're both going the same direction. So same dashes don't mean they're doing the same thing. Doesn't mean equatorial and axial. It means at this position, we'll say this is that 4 position and this is the 1 position. At the 1 position, our methyl is going down, 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 and up, up, down. On this one, up and down, down still means down. Over here on this one, I have up versus down and up and down. So I would actually redraw this nice and flat with a wedge for up and a dash for down. But interesting, my trans 1,4-dicyclohexane has the other chair conformer, which is super high in energy, because if I switch this one to the other chair, this one would actually become axial, and this one would become axial. And since I know that's unlikely, this is going to favor this particular chair. The trans one in that case is far more stable. But on the cis, it doesn't make a difference, because this one was down, the other chair it would be, or this one was equatorial. Sorry, this location is axial. On the other chair, it would be equatorial, and this one opposite flips. So you would always have one that's equatorial, and you would always have one that is axial on the 2 different chair conformers. Therefore, cis 1,4-dimethyl cyclohexane doesn't have a more stable chair conformer. Both are the same. And that's what we're kind of showing here on this thing. When that ring flip happens, we go from axial to equatorial and axial. These guys are equivalent. But on the cis one, equatorial and equatorial becomes axial and axial. We don't like axial and axial, so this ring flip favors the more stable chair. And other weird thing, the interactions you have when they're both axial almost make this particular chair impossible to stay. So we can almost guarantee when we have 2 different methyl groups on there, if you have a conformer where they're all axial or both are axial, it's not going to stay that way. It's going to go right back to the other chair. I'm going to draw it the way I like, because I can draw it faster, where those 2 groups, 1, 2, 3, 4, are equatorial. It's going to favor that tremendously. Alright, tert-butyl group drives the call always. So if you ever have a tert-butyl group coming off a ring, so let's say I wanted to actually draw this thing from just the name, I would actually draw it in more than one step, because I'd start by drawing the cyclohexane. And it says cis, tert-butyl, and 3-methyl, so 1 tert-butyl, and I'm going to draw it with a wedge. And I'm just going to do CCH3. 1, 2, 3. Since it's cis, I'm going to draw these both as wedges. And this other one is CH3. Alright, so that's what I'm going to draw. And I came up with this drawing from the name. So I'm going to draw my chair conformer. And I'm going to decide to make this position my 1 and this position my 3. Because they're easy to get to. They're both on the top of that thing. And on my 1 position, I'm just going to actually make this the 1 position. No particular reason why. It could have been this one, but I'm going to put this 1 position. And it says wedged up. But what I really want to focus on, I want them both on the same side. So if one's up, the other one's up. But I'm going to draw them both down because that puts this tert-butyl group equatorial. And we know we want the tert-butyl group equatorial. So I'm drawing this down, therefore I'm going to draw the CH3 down, so it's here. So cis, 1-tert-butyl, 3-methyl cyclohexane has both of those groups equatorial. And because it is a tert-butyl group, this pretty much doesn't happen. That ring flip requires way too much energy. In a mole's worth, it's going to happen enough that we could do chemically something with it, but it's 4,800 times more likely, at least, to stay in the more stable conformer. Okay, trans is a totally different story, though, because when it's trans, so trans is, we could actually view it this way in the ring, got my hydrogen up, the other hydrogen is down. Those are opposite, that would fit into trans. But we'd have the same type of thing. We'd want to keep this thing equatorial because this is a big bulky group. And this methyl doesn't matter, but in this case the methyl actually has to stay axial. Alright, turns out rings actually can be fused to each other. And it's interesting that, at least on a chemical structure like a calculate structure, we would draw fused rings more than likely like so, because it's easier to draw two hexanes. But what's weird is we could actually have done this with wedges. So having this wedged up and this one wedged up is totally different than having one up and one down. And they are two totally different molecules. And that's what we're seeing here. A trans ring has the H's on opposite. I have one H going up, one H going down. The cis, both the H's are going up with respect to their locations. So we get a weird little zigzag pattern. But rings do this, and we do actually have stability affected by it. Alright, so something we have to worry about on this. The three-dimensional structure is darn important on so many of our organic molecules, yet we're almost always going to draw two-dimensional things. So we want to be comfortable with it. So some of this stuff, and I have been teaching it flat on paper for a reason. I want you to be able to relate it to the flat nature. I don't want you to need to visualize 3 dimensions. But on many cases, it's a heck of a lot easier to see what's going on, or to help clear it up if you were to fire up your computer and do Avogadro. Now, I don't actually have live, active, good internet right now, but on all these, I could have actually typed in the names. So, in theory, I could... Let me see how my internet's behaving today. New. And import from a name cyclohexane. And we'll see if it pops up. Yeah, it's not finding it for me. Alright, but let's see. I think one of my other imports, no, I don't have a good way of doing it. But theoretically, if you're on a decent internet, you just type in cyclohexane, it should actually find it, because there are quite a few that are actually searchable on their little setup. But if you have to build it, or download it, or something along those, the PDPs, you can find a PDP for many of these compounds. I probably will even have it added to the page, or at least I could. So if you need it, send me an email and I'll send you the file that you need. So if you want me to make a molecule, just ask me for the molecule and I will send you a PDB of it. Alright, that gets us done with Chapter 3.